Okay, this video is to give you some background and additional information and some homework help for Webassign 15A on equilibrium constants. And we'll have about 3 or 4 topics I want to cover briefly, and then we'll look at some of the homework problems. So let's take a look at first of all, let's take a look at collision theory. Collision theory has 3 main components to it. It comes up a little bit later on in the chapter, but I find it helpful to talk about it right up front here. The first point we want to talk about collision theory, first of all, has to do with chemical reactions. In order for chemical reactions to occur, particles have to collide with each other. And so when they collide with each other, there's the possibility for a reaction. So that's the first part. There has to be a collision. And it's almost kind of too obvious, but a lot of times with theories we have a very obvious statement right up front. The second part of collision theory is that there has to be enough energy in order for that collision to be successful. If those 2 molecules just kind of come in and gently bump into each other, they'll likely just bounce off. So they have to be able to break some bonds. There has to be enough energy coming in for those 2 particles to kind of shake things up, break some bonds, allow some new bonds to form. So they have to collide. They have to collide with enough energy. And then they have to collide with proper orientation. And orientation is just how they're turned towards each other. Let's see if I can grab a couple of molecules here just as an example. So if we're expecting the oxygen on the end of this molecule right here to react with the hydrogen on this molecule, and they collide like this, that's the proper orientation. You know, with enough force, they can react with each other. But if they come in with the 2 oxygens oriented towards each other, and that's not the intended reaction, the expected reaction, then that orientation is not favorable. Even if it's coming in and it's going to collide, even if it's coming in with enough energy, if it's not hitting the proper orientation. So they have to collide, they have to have enough energy, and they have to have the proper orientation. And there's different ways that we can control that. Some of those different aspects right there. And that gets into our next little concept, which is the rates of reaction. As far as rates of reaction go, it's how fast the reaction goes. In what ways can we control the rate of a reaction? So we can, and generally when we talk about this, we talk about increasing the speed or decreasing the speed of the reaction. So if we want to increase the rate of the reaction, we can do that using several different factors, properties, characteristics, things like that we can change. So we can increase the rate, one, by increasing the concentration of the reactants. And if you go back to collision theory, you know, collision theory has to do with collisions, energy, and orientation, then we can connect to that. By increasing the concentration, we're getting more collisions. And if you get more collisions, then you're going to get more possible reactions. So by increasing the concentration, you're able to increase the number of collisions. And generally with increasing the concentration, that might be increasing the molarity. You know, so add more solute is one way you could do that. So for aqueous substances, you can do that. And then if it's a gas, something that's in the gaseous state, you can do that by decreasing the size of the container. So you can take a gas that's in this size of a container floating around like this, and you can push that piston down. And as you push that piston down, the gas molecules are in a smaller amount of space, and they'll bump into each other more often. More collisions, faster rate of reaction likely to occur. The second point is the increase in the temperature. By increasing the temperature, remember from kinetic molecular theory that temperature is proportional to the average kinetic energy. And so with an increase in the temperature, you get an increase in the average kinetic energy. That means, since kinetic energy is 1/2 mv squared, that means that the molecules are going to be moving faster. And if they're moving faster, they're going to collide with each other more often. You know, they're going to bump into each other more often if they're moving faster, and with more force. So that means there's more opportunities for that activation energy to get the reaction going, to take place. Third point here is the surface area. We can increase the surface area, which means spread the material out, right? So if we increase the surface area, instead of, say you want to start a campfire, instead of starting with one big log of material, if you start with much smaller pieces, they could be the same mass, but if you start with much smaller pieces, a lot more of the necessary reacting oxygen can get to those pieces, and you'll increase the rate of the reaction. And then the fourth one is to add a catalyst. And a catalyst simply is there, that's its job, is to increase the rate of the reaction. And it generally does that by providing some other reaction, some other pathway that's going to have a lower activation energy. And so that's how that often works. Sometimes it has an impact on the orientation that we talked about just a few minutes ago, with collision theory, collisions, energy, and orientation. Sometimes it has an impact on that as well. We'll deal with rates of reaction a little bit later on as well, but we need to talk about it now because the major topic of the chapter is chemical equilibrium. And equilibrium, the equal part of equilibrium, is when you have equal rates of forward and reverse reactions. So having just talked about rates of reaction and how we can control those, we also need to recognize that at some point many reactions are going to have established an equilibrium. So the equal part of equilibrium is equal rates. It's not equal amounts. It's not equal grams. It's not equal moles. It's not equal concentration. It's equal rates of both the forward and the reverse reactions. When we use in a chemical reaction, if we have something, like A plus B produces C plus D. In the past, we may have only written a single arrow. What's very common for us to do in this chapter is to use this equilibrium arrow, this reversible reaction. So a reversible reaction means that A and B can collide to form C and D, but there's also a possibility that C and D can collide and revert back to being reactants A and B. That's called a reversible reaction. And there are some reactions that are not reversible. If you get our non-reversible reactions are those that, remember our driving forces we talked about earlier in the year, those that form water, those that form a precipitate, those that form a gas. If you form one of those, it's unlikely that they're going to revert back to being their reactants. So they're not generally reversible reactions, but that still leaves a lot of reactions that can be reversible. When they get to this point where they've reached equilibrium, it's often referred to as dynamic equilibrium, because the dynamic part, dynamic kind of, means constant activity. Okay, what that implies here is that the reaction of A and B to C and D doesn't stop once it gets to equilibrium. That keeps happening, but C and D, going back to A and B, happens at the same rate. So the end result with these equal rates of forward and reverse reaction is that the amounts of A and B and the amounts of C and D don't change. They're not equal to each other, but the amounts don't change, even though they keep bumping into each other and reacting and reversing that reaction. So that's the idea of equilibrium. The main part of this Webassign is to describe equilibrium in a quantitative way, to give some numbers to crunch, to talk about chemical reactions in a manner that allow us to quantify what's going on in the chemical reaction. So to do that, we use equilibrium constants. And equilibrium constants are going to be written up in the same kind of fashion. We're going to start with the generic equation. A plus, we'll use the A plus B again. A plus B produces C plus D. And the coefficients in the equations become relevant as well. So we're going to put some representations for coefficients. Lowercase a, lowercase b, lowercase c, and lowercase d represent the coefficients. And when we write an equilibrium constant, we simply are going to take these amounts and write an equilibrium constant. So the Q here means the constant. and the EQ means equilibrium. So equilibrium constant equals, we're going to move our products to the top, and we're going to use these square brackets. That means molar concentration. And then our reactants are going to go on the bottom. And then any of our coefficients that are in the equation. If it's a 1, we don't normally show it, and we wouldn't use it here, but the coefficients become exponents, superscripts in our equation. So lowercase c, lowercase d, lowercase a, and lowercase v. And that's how we write an equilibrium constant expression. And so we'll take a couple examples and then move on over to Webassign here. Let's see here. One thing we want to, so we'll just start with a simple little reaction. It's similar to what we just did there, but I want to try it here with these little cards. Here's our chemical reaction to start with. A and B produces C plus D. And when we get that chemical reaction going here, we've got, I think I lost my arrows. So kind of lay these right on top here. So A and B reacting to form C and D. When we write the equilibrium constant expression, KEQ, the C and D get shifted to the top and the A and B get shifted to the bottom. So we're going to kind of move them counterclockwise like this. So we're going to move them counterclockwise and write our equilibrium constant expression. So that's products over reactants. Now that's not really our equilibrium constant expression still, because it still kind of looks like it's part of the equation. So we're going to swap that out and use those square brackets, and we've got the C and D in the brackets with the coefficients, and then we've got the A and B with the brackets and the coefficients. So that's how we write an equilibrium constant, similar to what I just did with the paper there. Let's talk about one more thing with equilibrium constants, and that's what you do if there's a variety of states of matter. So this is calcium carbonate as a solid, HCl aqueous, calcium chloride aqueous, CO2 is a gas, H2O is a liquid. When we look at equilibrium constants, it wasn't mentioned before, when we look at equilibrium constants, we write the products over the reactants. But another important point here that needs to be made is that we only do these equilibrium constants with those substances that have changeable concentrations. Those are things that are aqueous and gaseous states of matter. Do not include those things that are pure solids or pure liquids. So we're just going to stick with those things that are gases and aqueous. So if we now look at this equation again and do a similar kind of a thing that we had just done with the other one, we've got our calcium carbonate and hydrochloric acid, and our products, calcium chloride, H2O, and CO2. And we're going to create our KEQ expression. So we're going to take our products on top and our reactants on the bottom. So we're going to shift those products on top, reactants on the bottom. Put a dividing line there for the numerator and the denominator. And we want to swap out, remember we want to use the notation. Oh, a couple things here. Notice that CaCO3 here is a solid. So we don't want to include that in the expression. So let me kind of tuck that behind here. We're only going to use the HCl on the bottom. And on the top, H2O is a pure liquid. So we're going to tuck that one away. We're not going to use that in our expression either. So we're just going to use the CaCl2 aqueous, the CO2 gas on the top, and the HCl aqueous on the bottom. So on the top, using the square brackets, that becomes CaCl2 and CO2. And on the bottom, that becomes HCl. Notice that the 2 as a coefficient in the equation becomes an exponent down here. So that's how you do it with different states of matter. Now in Webassign, you've got a variety of problems that, you've got some early multiple choice questions, and then here in question 7, you've got some given values of KEQ, and you're asked to make a prediction for the, let's see, zoom in here a bit. There we go. You got a number. Try and get it focused there a little bit better. So 5.6 times 10 to the 3, 3.1 times 10 to the minus 23. Remember, equilibrium constants are products over reactants, right? So if you've got a really small number, like times 10 to the minus 23, how do you get such a small number? That means the numbers in the bottom are really big, and the numbers on top are really small, because when you divide them, you get a really small number, like times 10 to the minus 23. And so if you have that kind of a situation, times 10 to the minus 23, that means you got a lot of reactant. The stuff on the bottom is the reactants. And so that's how you predict whether it's favoring the products or reactants. And then the calculations, 8 gives you an equilibrium mixture, 9 gives you an equilibrium mixture, and you plug those in. 10 and 11 give you equilibrium mixtures, and you're able to plug all those in and either solve for KEQ or possibly solve for like the concentration of CO2 if they give you the KEQ. That's just using your math skills right there. The trickiest one is number 12. So let's take a look at that one together. And let me get some. I'm going to get some line paper for number 12 here, and switch over to the marker. So in number 12, here's the. I'll bring this up here so we can take a look at it. In this case, in letter A, it's being done like the others here, number 12. They give you some equilibrium situations, and you're going to solve for the equilibrium constant, letter A. So that's pretty straightforward, pretty routine. Let's go ahead and write up the equation and kind of see how that works out, though. So we have, hold that back so it's out of the way. So here's our chemical equation. I'm going to omit the states that matter. They're all gases. So I'm just going to kind of skip past those. And so we have H2 plus CO2 in a reversible reaction with H2O and CO. And then from that point we can write up the KEQ. KEQ is equal to the concentration of H2O, the products on top, times CO over the concentration of H2 and CO2 on the bottom. Products over reactants. You can then take the 0.1 moles, it's in a 1 liter container, so 0.1 divided by 1 liter is still 0.11. And that'll be both the CO and the H2O, so those are the top numbers. And then the 0.087 also is the same for both H2 and CO2, so that'll go into the bottom numbers. And so that's pretty straightforward. That's pretty easy to figure out. And you're going to figure out the KEQ. So plug in those numbers and then get a result over here. We're going to use that in part B. So that's part A, solve for the KEQ. And then in part B, we're going to set up what's called an ICE, I like to call it an ice box. It's also called an ice table. ICE is an acronym, well, sort of an acronym here that stands for initial change in equilibrium. So I'm going to rewrite the equation here. Shift this up here a little bit. I'll rewrite the equation. So we have H2 plus CO2, our equilibrium arrow, H2O plus CO. And then they say in this problem here that 0.08 moles, and notice this is worded a little bit differently here. Suppose 0.08 moles is placed in a 1.4 liter container when equilibrium is achieved. In other words, this is the first problem you've got to that hasn't said at equilibrium or an equilibrium mixture like that. It's the first one where it's not necessarily at equilibrium. They want to know what the amounts of CO and H2O are, so they're giving you some of this. Obviously it's not at equilibrium because it hasn't reacted yet. When it reacts and gets to equilibrium, how much of this will there be? That's what they want to know in terms of moles. So what we're going to do is set up what's called an ice table, an ice box. I like ice box. I think it's kind of catchy. First thing we want to do is figure out the concentrations. So we have 0.080 moles of H2, and it's in a 1.4 liter container. Now I don't know if those numbers are going to stay the same for you or not, but I'll just work with these numbers, and if your numbers are different, then make the necessary adjustments. And the CO2 is also 0.80, H2 and CO2, in the 1.4 liter container. So that gives us the moles per liter. When we work in the ice table, the ice box, it's kind of nice to work all that in molarity units. That's pretty standard practice right there. So 0.08 divided by 1.4 is 0.057. We'll keep 2 sig figs. Remember that 0 is a placeholder. So they're both going to be 0.057. All right, so those are the concentrations, and we don't have any of this. Okay, there's none of that to start with. So what we're going to set up is an icebox. And so I've got an I and a C and an E that I want to set up. Shift up here a little bit. And the I stands for initial. And the C stands for change. And the E stands for the chapter title here, equilibrium. So initial, change, and equilibrium. The initial amount we just calculated right here. So normally this would be right up underneath the equation, but I had to do a little bit of preliminary calculation work. So this is going to be 0.057. This would be 0.057. And this is 0 and 0. Now we don't know how much it changes exactly, but we do know that based on the balanced equation, for every one of these, there's one of these that will react. And one of these will be formed, and one of these will be formed. So they're all related to each other in a similar way. So we're going to use X to represent the amount of H2 that reacts. If X amount of H2 reacts, then X amount of CO2 reacts. X amount of H2O is going to be formed, so I'm using plus X. And X amount of CO will be formed, so I'm going to use plus X. So that means at equilibrium, I have 0.057. The initial is this. It's going to change by this much. So at equilibrium, I have 0.057 minus X, 0.057 minus X, and then 0 plus X is X. 0 plus X is X. I now have some equilibrium conditions, some equilibrium amounts. So I can now take my KEQ, let's write that up again so that we can see what's going on. We're going to take that KEQ expression from up above. I'll just rewrite it here. CO, H2O and CO on top, H2 and CO2 on the bottom, CO2. And I can now substitute these numbers in. So up top it's going to be X times X, and on bottom it's going to be 0.057 minus X minus X, and 0.057 minus X. Now you recognize that those are squared terms. So that's going to be X squared over the quantity 0.057 minus X, that quantity squared. Now you found KEQ up here. So what you found as your KEQ for letter A, you're going to incorporate that as the KEQ on the right-hand side of the equation down here. So whatever you solve for up here, I think it's in the 1 point something, like 1.6, I believe, somewhere is what I solved for earlier. So you're going to have a value up here that you will know. And from that point, you'll be able to kind of solve for X. Now it looks kind of like a quadratic, you know, it looks kind of like a nasty little calculation that you have to deal with, but it's really not so bad. If this is in fact 1.6, I don't remember if I'm remembering that correctly, but make sure you do the work correctly. So if this is 1.6, all we have to do to simplify the math here is take the square root of both sides. So if I take the square root of this side, take the square root of that side, then what I'm left with on the right is X over 0.057 minus X is equal to whatever the square root of 1.6 is. So let me find that over here. That is 1.26. So it's only got 2 sig figs, but I'm going to go ahead and keep the 1.26. Remember, those are the 2 sig figs right there. And now you can solve for X. And I'll leave that part to you guys. When you solve for X, so, you know, do the math, you know, bring this over, distribute that, collect your X's, solve for X. So when you solve for X, it'll take a couple of steps there, but when you solve for X, that's going to represent the number of moles per liter of H2O and CO right up here. They wanted the moles, not the moles per liter. So once you solve for X, it'll have units of moles per liter. Don't forget to multiply that answer, going back to the problem here, don't forget to multiply that by the 1.4 liters. If I multiply it by the 1.4 liters, the liters cancel out, and that will give me the moles. And they both solve for x, right? When you solve for this, they're both x. So when you solve for the concentration of CO, you will also have the concentration of CO2. These two will be equal to each other right here. Okay. So anyway, that should do it. It's kind of a tricky problem, so I wanted to kind of help you work through that one here with the video. All right. So you do the math, and I think it'll work out for you. That'll do it.